Hey everybody, welcome to Control System Analysis and Design. We're going over Routh tables and design using them again. So this is our second example. If you want to see another one, you can look at one of my other videos. So we're given this transfer function, and it's part of this unity feedback system. So in order to solve this, you can use g over 1 plus gh, which is the equation for reducing this block diagram to just a single block, just like this. And you should know how to do this, so I'm just going to skip to what the answer is. If you do all this work, you're going to end up with k of s plus 2 all over s cubed plus 2s squared plus k minus 1 s plus 2k. And if you don't know how to do that block reduction, go watch one of our other videos and you'll be able to learn how to do that. But here is the basic function we're working with. In order to use a Routh table, you just look at the denominator here, which is just this part, and you can completely ignore the numerator. So setting up the Routh table now, 3s cubed, s squared, s1, and s0. So we have to find, what we're supposed to be finding in this problem is the range of k, which makes the system stable. The system stable. So if you want to think of this in another way, if you're looking at the complex plane with j omega and real up here, you're looking for the range of k that keeps all poles on this half of the plane, or on the j omega axis, depending on which criteria you use. But if there's any pole on the right half of the plane, or any sign change in the first column of the Routh table, basically, then you have an unstable system. And you have to find which k's keep that from happening. So going in here and creating our Routh table, you should be familiar with this already. We've got k1 and k minus 1, and then 2 and 2k. Now you might be tempted, if you're familiar with this at all, to go into an inequality that makes all these k's positive, these values positive for whatever k. Don't do that. This part of the Routh table, or anything over on that side outside the first column, is irrelevant to figuring out whether a system is stable, or the stability criterion. So you're going to go down here, you're going to create the matrix, negative, and 1, k minus 1. I go over this in a different video, the system, if you're not familiar with it. 2 and 2k, just like that, all over 2. And if you solve this out, it's going to be equal to negative 2k minus 2k plus 2 all over 2. And that is going to equal negative 1. And we're done. Now that happened kind of fast. I'm sorry about that. But if you look at this, you're trying to find the range of k's that will make the first column greater than 0, because these are both positive. In order to make sure that it's stable, there can't be any sign changes in the first column. But right here, we got a negative 1 even after putting k's in there. The k's cancel. So the k's are irrelevant to this problem, because no matter what k's you use over here, whatever range of k you use, you're always going to end up with a sign change in the first column of this table. So no value of k makes the system stable. And we're able to stop right at that point at negative 1, because we just proven that no matter what happens, we're going to have that sign change. It doesn't matter what happens in the rest of the Routh table, over on the right in these columns, anything at all. That sign change, that constant, after having used k's in the matrix, means that there's nothing we can do to stop it from happening. And it could go up here too. If for some reason the denominator had a sign change and we had plus, and then say instead of a plus here we had a minus, you can immediately stop right there and ignore the k's and the rest of the work just by writing down the first two columns, because this sign change makes the system unstable. So as soon as you find a sign change of a constant, you can stop right there. The system is unstable. There is no k that is ever going to make it stable. There's no gain that you can use.